Greetings, chemists. This lecture will be on nuclear radiation. And it started with an observation made by people who were digging up a rock that contained uranium. And they found, I think the scientist involved had been using uranium in experiments where he was they kind of knew that it shined out some kind of radiation because they could put it near a phosphorescent screen, this rock, and the screen would light up. A phosphorescent screen is that when radiation hits the screen, it creates little color splashes. And so they were seeing little sparks of dots of light here and there. And he found that even when he left it up against a wall, this was a completely accidental find, that he had it in a bag, he was like wrapped it in cloth. And even through the cloth, it was lighting up a phosphorus screen that he had stored nearby. And he said, wow, that's a really interesting phenomenon. So people started looking at this uranium. One of the things they noticed is that uranium rocks often have splotches of different elements on them. Okay, so the rock is not like a uniform mineral. There are pieces of uranium, there are pieces of thorium, there are pieces of other metals, etc. throughout it, or little areas of them, and that was kind of interesting. But that if you took the uranium rock and purified it, you just cut out the parts that are perfect, just uranium, let's say that's pure uranium and not any of those other splotches, if you leave it out long enough, it will actually start to develop splotches of other elements. And this was sort of puzzling. So people made an assumption, these chemists made an assumption that there must be a transfer of some kind of nuclear charge happening. So what we know is that to be an atom, to be a uranium atom, you have to have 92 protons. If you don't, you're some other atom, right? The thing that makes a specific atom that type of atom is the number of protons, the atomic number. So somehow, for this uranium to be developing other elements and not like absorbing them from the atmosphere or something, which they determined was not happening, it must be changing the number of protons in some of the atom's nuclei. It must be converting them somehow. So they being these early scientists, studied this and studied this and studied this, and they came up with there are several ways that atoms can change their nuclear charge. So for instance, if you had a bunch of protons in a nucleus, because remember, it doesn't matter what the neutrons are doing. The neutrons are just there, right? There are several ways. If the nucleus, now I'm not talking about the whole atom, I'm just talking about the stuff in the middle, in the center, in the nucleus. If you were to spit out a proton, for instance, and be left with, what is that, 3 left? Let's see if I can actually draw this the same way I had it, right? Where you have like that gap there and there's no more proton. Okay, that would change your nuclear charge and turn you into a new atom. And maybe they said we're ejecting protons. Or what if you were to absorb a proton? You would gain more of them. What if you were to lose, sometimes you can do it, there's a form of radiation where you spit out a negative charge, where you take something neutral, like a neutron, and it loses a little negative charge, and so it becomes positively charged as a result, like that. That's called beta radiation, okay? That was one thing they observed. You could also capture an electron. If you captured an electron, let's say that this proton, which was positive, saw an electron out here and sucked it in and captured it, that would neutralize that proton and create another neutron, right? So there are many, 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 many modes. We're going to talk about 3 of the most common, which are the following. They said that one kind we observe lots over and over and over is that you have some nucleus with a whole bunch of particles. And in fact, so many that pretend that I drew even more than this, okay? And at some point in time, this chunk falls out of the nucleus or gets ejected from the nucleus, gets shot out of the nucleus, if you want to think of it that way. What is that chunk? It's this chunk. It's 2 protons connected to 2 neutrons. We actually see this happen fairly regularly. This is a pretty common type of radiation where a nucleus shoots out this chunk of 4 particles. If it does, we call that alpha radiation. And so this is sometimes referred to as an alpha particle. You will note that it has 2 protons and 2 neutrons, which is the same as a helium nucleus. And you will sometimes see this written as ejecting a helium ion, because it doesn't take electrons, it just takes the protons and the neutrons. Okay? This is a type of way that a nucleus might, like a uranium nucleus perhaps, could shoot out a couple of protons, and if it did, it would lose 2 protons, and now it wouldn't be uranium, it would be thorium. Thorium is number 90. Okay? Another way, and I mentioned it here, where you shoot out an electron, so let's say you have the same big honking nucleus, okay, and one of the neutrons shoots out a little negative particle, which would basically be an electron. We can think of it as having the same mass as an electron and the same charge. Now, it's not technically an electron because it came from the nucleus, right? And electrons are not in the nucleus by definition. But if it did, it would then create a new proton in its place, right? Taking a negative away from a neutral turns it into a positive. And this is referred to as beta radiation. And this, I know it looks like an electron, but we often call it a beta particle. Okay. Well, another thing that can happen, big honking nucleus, is sometimes these nuclei don't actually eject particles, but they eject light rays. They just shine out a very strong light. Maybe you could talk about ejecting a photon, which is a particle, but it technically has no mass or charge. So it gets rid of high energy light. And the type of light given off by these atoms is, if you remember from our discussion of light rays, is a gamma ray. And so this is gamma radiation, which is the smallest light ray we know of and the most dangerous, right? Because smaller wavelengths is higher frequencies, which is higher energy. So you would say this is a gamma photon, or a gamma ray, if you prefer. There are others. Like I said, there's electron capture, there's, you can emit things called positrons, which are like beta particles, but positive, they have the same mass, but they happen to have a positive charge. Neutrinos, all kinds of things. But we, for the purposes of this class, we are going to focus on these 3 types of radiation. So let's look at what do they do. An alpha particle, remember, is 2 protons and 2 neutrons. And just like a helium nucleus, it has 2 positive and it has a mass of 4. And we will often actually call it an alpha particle or a helium plus 2 particle, because it's identical to a helium plus 2 particle. Alpha, by the way, is how the Greeks wrote their A's, so that's a Greek A right there, if you want to use that letter for it. This is big and heavy. Okay, this, of the 3 types we're going to talk about, it has 4 mass. That's gigantic. So big, heavy, and I'll put in that it's also slow. Of all the types of radiation, it does not travel very fast compared to the others. So it has the lowest energy. Because of this, alpha particles tend to not be very dangerous. A lot of times when people talk about uranium or talk about plutonium or other radioactive elements, and they talk about radiation, there's this idea that this is a pretty dangerous type. It's going to do damage to your body, etc. So to give you an idea, if this pencil was an alpha emitter, and I put this stack of papers here, though it might be shooting out alpha particles, they might make it this far. They might not even make it this far. They might hit an air particle in between and get eliminated and not do anything, right? If I put my hand here, they would probably hit my hand, but they probably would just destroy like a skin cell, right? It would be, I would be losing some dead skin cells off the surface of my hand, but it probably would not do any long-lasting damage to my body. Alpha radiation is so slow and not penetrating that if it's outside of your body, most of the time, I'm not going to say always, but for the most part, it is not dangerous if kept outside your body. So it doesn't penetrate farther than a couple centimeters. And that's in air. Air is enough to block alpha radiation. Now, that's not to say it isn't dangerous in some ways. So, for instance, if you had a little chunk of a material that shoots out alpha particles, holding it in your hand or near your hand is probably not too dangerous. But if you were to grind it into a powder and swallow it, and it was inside up next to your organs where it could just shoot these alpha particles directly into your organs, it could actually do a significant amount of damage. And there were, I think, assassinations carried out, like, KGB assassinations and things, where they would take alpha emitters and grind them up and put them in people's food, and the person would eat it, and later they would get very sick, and by that point it was too late. The radiation was inside their organs, inside their bodies, doing a lot of damage. So if you were to inhale, if you were to go outside in a place where there had been some nuclear fallout and these alpha particles were in the air, or these materials that emit alpha particles were in the air, and you inhaled it into your lungs, it could do a lot of damage to your lungs. So that's the danger of an alpha emitter. Okay, what about the beta particle? A beta particle is basically like an electron. It has the same charge of the electron. It has the same mass. So if you put the charge number down here, it would be a -1 charge. But if you put the mass number here, it would have no mass. And beta, the Greeks wrote their B's like this, little tail, and we'll use that for the beta radiation. Okay? And so you can write beta particles as 0, -1, or you can write them technically as electrons. I have seen chemists write their beta particles like an electron. I just want you to know it does not come from the electron cloud. It comes from the nucleus. Make sure you know that. They're small. Now, electrons have some mass, but it's like thousands of times smaller than a proton, so we don't typically write the mass on it. We assume it's a relative mass of 0. If my pencil was a beta emitter, and I put my hand here, they go zipping through my hand. They could actually do some damage to the hand. Okay? They are not impossible to block. If I were to take a sheet of tin foil, or a sheet of aluminum foil and put it right here, it probably could not penetrate through that very well. If I had a sheet of plexiglass, a little thin sheet of polymer, and put it here, I probably could stop with a couple of centimeters of polymer the beta particles. And just like alpha particles, if you were to swallow a beta emitter, it could do an awful lot of damage to your insides. But from the outside, if you were to wear, your tinfoil hat, because you also are a conspiracy theorist, you would also be blocking beta radiation. So small, faster, and higher energy. Okay? You can stop it with plexiglass or tinfoil. Metal will stop beta particles. More dangerous. And the last one, gamma. So a gamma particle does not actually have any charge, and it does not actually have any mass. It's just a ray of light. And the letter for G, this is a Greek G, would be the gamma. That's a gamma. Okay? It's light. We talked about light rays. It's very penetrating. So if I put this pencil here and it was shining out gamma rays, and I put my hand, they go right through my hand, give me all the cancer, right? They're very, very toxic, these gamma rays. If I were to put a sheet of plexiglass in the way, a sheet of plastic, a sheet of metal, probably goes right through it. To stop the gamma, you would need about a few centimeters like this of a very, very dense material like lead. Lead can stop gamma. So like when you go to the dentist's office and they put the lead apron on there, that's X-rays, not gamma rays, but it would work probably similarly for gamma rays. So it's light, it's very penetrating. You can stop it with several centimeters of lead or a similar material, right? If you had, I think I've mentioned this in a previous video, but when I worked at when I was a student at UC Irvine and I took my radioisotopes lab, we were dealing with gamma emitters all the time. They take their nuclear reactor and they put it at the bottom of this 25-foot pool of water. So water is not as dense as lead, but if you put enough of it in between you and the gamma rays, then it will stop them eventually. So very dangerous stuff, gamma emitters. And it's not like the Hulk. If you absorb a bunch of gamma rays, you don't get superpowers, you just kind of die. So nuclear radiation. Why does all this stuff happen? So scientists study atoms, and they look at atoms that are stable, because not every atom is stable. For instance, carbon with 6 protons and 6 neutrons would have a mass of 12. That atom is very stable. It does not fall apart. It does not give away alpha radiation. It does not give away beta radiation. It does not give away gamma rays. Okay? Carbon, even when you add an extra proton or neutron to it, when you make it carbon-13 is still reasonably stable. But if you add one more neutron to it, it becomes very unstable. Well, I say very unstable. It becomes unstable enough to emit a beta particle and shine out or shoot out a beta particle. All right. So it seems to be related to the mass. And so what scientists do is they create this graph of an atom with a certain number of protons versus a certain number of neutrons. And they plot which ones are stable. We only put a dot on this graph if that combination of protons and neutrons is stable. And I'm not going to get into it. It goes all the way up to like 140. Or this graph does, and I'll go all the way up to 90 over here. So if we look at the first 90 elements, let's say, right, protons 1 through 90, what we see is something like this, and it's not perfect, and then it does one of these, like so, and I should put the 90 in closer, but this is the general shape of the graph. For a while, that line, this will be a line with a slope n equals 1, where they have the same number of neutrons as protons. That's this line. And at the very beginning, it's pretty close that most atoms, like carbon has the same number of protons and neutrons, and it's stable. It's right on the line. But after a certain point, that line starts to curve upwards. And the more stable atoms, like uranium up here, if you look at uranium, uranium-92 has a mass of 138. It has way more neutrons than protons. 238, excuse me, I should say. That's more than double 92, right? So it's not a one-to-one proton to neutron ratio. I think it's 92 and 150 or something, 140 something, 146. Yeah, 104. So it has this, just to put the numbers to it, has 92 protons and 146 neutrons. So you can see that line bending up towards that. Well, the term for this, they call this the band of stability. The idea is that at low ratios, at small atoms, it's much more stable to have about as many protons as neutrons. Sometimes we refer to neutrons as the nuclear glue. It's what holds those positive protons together. The more protons you try to cram into that nucleus, the more positive charges that are repelling each other, the more neutrons you need, nuclear glue, to keep those protons from pushing each other apart. And if you exceed that, well, sometimes when you have too many neutrons even, when you get too many of one or the other, either too few protons to neutron ratio or too many proton to neutron ratio, then that atom becomes unstable and it starts spitting pieces out until it gets back to a stability like we see here, where it's finally got the right ratio of glue to positive charges, you could say, to hold itself together. All right? So above, what do we see? Like in the lower regions for the smaller atoms, you tend to see beta radiation. And at the upper reaches, you tend to see more alpha radiation. And and gamma, I would say you see at the upper ranges as well. Okay, so if you're not ejecting particles, sometimes you're just losing energy. So a nucleus can get rid of its energy by shining out these high energy gamma rays. All right. So all of this radiation is an attempt to take an unstable atom that had too much in its nucleus and inject that energy in some way or another, either by ejecting energized particles like an alpha or a beta particle, or by shining high energy light. Okay. And that's going to be the lecture on nuclear radiation.